Hi folks, my name is Bobby Kubor and I work as a solutions architect out of Sydney, Australia. And before we get started, I just wanted to start with a bit of a demonstration. Now, I think it's fair to assume that something like that may have required some previous robotics knowledge or experience, or that robot may have cost a fair bit to put together. Commercial robotic arms these days usually start at about 10,000 US dollars and work their way up from there. Interestingly enough, neither of these was actually the case. I was able to put together this robot with no previous robotics knowledge or experience, and essentially it cost somewhere between $500 to $600 to build. All of the parts that you can see or that you saw in the video are printed on a home $200 3D printer, and including the motors and some of the drivers, the whole thing costs somewhere between $500 to $600 to build. Now, all of this came about after asking one very simple question, and that is, how hard can it possibly be? For those of you watching that consider yourselves builders, you might be fairly familiar with this phrase. I know that I certainly am. The cloud and the open source community have really opened up the portfolio of technologies that were previously unavailable to developers. And as a result, with the number of options available and with the wealth of information online, it's hard not to underestimate the difficulty of leveraging emerging technologies. Now, occasionally this phrase gets us into trouble, such as potentially overcommitting to an over-optimistic timeline for a technology that we don't know much about, which usually results in a team of angry developers at 3 o'clock in the morning. But yet lessons learned are quickly forgotten, specifically in my case, where I was out to lunch with a friend mid last year who previously worked in the rehabilitation field, and we got into the topic of technology. And she asked how difficult it would be to use robotics to assist those with mobility difficulties. Now, I naively responded, how hard could it possibly be? I admittedly probably shouldn't have been responding. I have, like I said before, no background or education in robotics. I've never really built anything with my hands before, and I'd never really used a soldering iron. To be honest, I didn't know the difference between a volt and an amp, but I still wanted to give this a go. I wanted to give it a shot. I figured maybe I could build a robotic arm that would be able to see objects and potentially grasp those objects, possibly move them around and manipulate them. So I decided I'd do what every other builder does. It's a well-worn path, which is usually to jump online, look through some open source code, hopefully find something that meets 50% of what I need to get done, and then learn the minimum required to hack the rest together to get the job done. Now, when I first got started on this, I noticed a number of potential showstoppers that would be fairly familiar to any organization that's looked at leveraging robotics. So the first, which was the biggest showstopper for me, admittedly, was around cost. As I mentioned before, usually robotic hardware, specifically commercial robotic arms, start at about 10,000 US dollars and can work their way up to 6 figures for industrial spec heavy-duty robot arms. This was obviously well out of my price budget, but also out of the price budget of a lot of organizations that are simply looking to experiment and understand the art of the possible when it comes to robotics. So from there, I went and purchased a toy robotic arm, one that's programmable so I could understand what was involved in the software aspects of robotics. Now, this brings me to my next point, which is that testing out robotics can certainly be hazardous to your health. So if you think about a 1-ton industrial spec robotic arm, for instance, that you deploy code to incorrectly, it could certainly do some damage to yourself or your surroundings. Now, in my case, with my toy robotic arm, when I deployed code incorrectly to it, it slammed its head into the coffee table, taking a massive chunk out of it, resulting in me being banned from doing any testing, further testing in the living room. So the next thing I did was take a look at simulation environments. I figured this was a good way to get started in a virtual environment which seemed like a safer way to do so, and I wouldn't have to cough up money for robotic hardware up front. Now, one of the issues here was around the compute requirements for complex simulations. There's definitely a considerable amount of compute resources required to run these simulations, and I didn't have that localized hardware. So on top of having to purchase computer hardware, I'd need to dual boot the laptop, I need to install another OS, I need to install multiple software frameworks and juggle different versions of packages. It all admittedly seemed like too much effort. Now, in addition to this, these difficulties, there are other factors that businesses face, such as requiring machine learning expertise to be able to build intelligent robotic applications, as well as effort involved to deploy these applications to fleets of robots. For organizations that already have leveraged robotics and have fleets of robots in their organization. So I sort of had a problem here, mainly around cost, and some people would say around safety. That's pretty much where I parked my project. That was about mid last year. And the good news is that at the end of last year, during AWS reInvent 2018, a new service was announced that promised to remove a lot of these showstoppers and allow me to progress this project. And that service was AWS Robomaker. Now, this service promised to allow robotic developers to be able to create intelligent robotic applications, test them out, bundle them, and deploy them to physical hardware or to similar virtual simulations. Robomaker actually extends one of the most widely used open source robotic software frameworks, the Robot Operating System, which is also known as ROS. Now, this is great for existing robotic devs that have an understanding of ROS. They can get started pretty quickly, but there's a number of additional capabilities that enhance that developer experience. So for instance, being able to use cloud extensions for ROS, which allows you to leverage existing AWS services. If you're an existing AWS developer, you'd be fairly familiar with some of these services that can be used, such as managed machine learning capabilities that we can build into robotic applications like Amazon Recognition or Amazon Lex to provide those intelligent capabilities. Additionally, we provide a managed development environment, which once again, if you're an AWS developer, you'd be quite familiar with. It's AWS Cloud 9, and it's fully configured for that robotic developer experience. We provide a managed simulation environment to allow you to take your robotic application and test it in multiple different scenarios in a safe manner. And then finally, we provide an over-the-air fleet management capability that allows you to deploy your robotic application to your physical hardware in a streamlined manner. So as I mentioned before, Robomaker extends one of the most widely used open source robotic software frameworks, the Robot Operating System. Now, ROS was found in Stanford Labs over 10 years ago and is now managed by the Open Source Robotics Foundation. ROS is essentially a meta operating system. What that means is that it provides a lot of the capabilities that you would expect from an operating system. Things like low-level device control, package management, and message passing between processes. One of the really cool things about ROS is the ability to break up your code into modular packages and then be able to share that with the open source community, or to be able to leverage existing packages from the open source community in your project. So a lot of the time, you're actually not starting from scratch. You're able to lean on the open source community for things like boilerplates. So basically, I had a path to progress my robotic arm project. I was looking at using Robomaker to provide a pay-as-you-go mechanism to simply be able to dip my toe in the water to determine if I was actually going to be able to build this robotic arm. I wasn't 100% certain whether I was going to be able to do so, so I wasn't really willing to commit a lot of money to robotic hardware to find out whether I could or not. So I figured this was a great way of getting started. Now, admittedly, I may have oversimplified how easy or how difficult it was going to be to build out this capability. If you think about it, as humans, when we go to reach out to grasp an object, there's actually quite a bit that happens subconsciously. If you take, for instance, picking up a glass of water, the first thing you do is to perceive that glass. You recognize that that's the object that you want to grasp, and then determine its distance relative to yourself. It might be too far away, so you might move closer to that object. You'll then basically determine the joint angles in your arm required to be able to reach out and grasp that object. You'll determine the orientation of your wrist as well as the approach and retreat direction. You'll assess the width of the object as well as the potential mass so that you're able to grasp it without crushing it or without breaking your hand, as well as not potentially dropping that object. And then you're doing all of this while you're aware of its surroundings. You want to make sure that you don't accidentally collide it into anything else. So there's actually quite a bit that goes into that whole process of building out the robotic arm. Now, the good news is that a lot of this has already been solved by industry. So this sort of problem is called the pick and place operation. And if you think about manufacturing or warehouses, they have robotic arms that simply perform this operation, whether it's picking up an item off a conveyor belt and putting it in a box or something else. So a lot of this problem has already been solved. And the other good news is that a lot of this is actually already open source. So we're able to grab the code for this and then reuse it and reapply it to specifically our robot that we have. So the first thing we actually need to do is to be able to visualize our robot. We need to be able to build a virtual representation of it so that we can use it in simulations. To be able to do this, we use what's called a universal robot description format, which is essentially an XML file where we're dictating the parts of our robot, the mass of each part, how those parts hang together, whether they're fixed joints or mobile joints, even things like sensors. So in our Robomaker IDE, we can put together this XML file, which we would then deploy into our robot visualization tool, which is called RViz. It's a managed component of AWS Robomaker, and it allows us to view our robot in 3D, where we can see it at all angles. We can make sure that it moves correctly, and we can even assess things like whether the sensors are working correctly. So what you can see in this picture specifically is a commercial robot that's wheeled up to an object. It's got a robot arm that it's pulling out to the side, and in its head, which is looking down, it's actually got a depth sensor that's able to determine where things are located within its view. It's able to determine objects in front of it, and it's able to build out that representation as what's called an octomap. It looks like what it's detected is a table with some objects on it that we can choose whether that's a collision object that we might want to avoid, or whether those objects on the table are manipulation objects that we might want to change or move. So once we've created that virtual representation, it's time to spawn it into a simulation. Now, we could take our robotic application and deploy it to physical hardware, but one of the main problems that we're going to have here, other than safety, is the ability to cycle quickly through multiple different scenarios. So if you have 20 different scenarios that you want to test your robot in, having to move that physical robot from scenario to scenario is going to slow down that robotic development. Being able to create 20 different scenarios and simulations allows us to spawn that robot more quickly in these different scenarios and be able to iterate on our robotic development much quicker, because we're going to be able to get that testing feedback much quicker. With simulations, we can create 3D worlds where you can dictate the terrain, physics properties such as gravity, friction, or even the different types of lighting. Now, the great thing about Robomaker for simulations, as opposed to using a local workstation, is that ability to spawn simulations in parallel, scale out as many simulations as required, collapse all that compute back down, and collect the feedback required to iterate on development. Now, there are some robotic projects where simulations are absolutely critical due to certain physics properties that can't be emulated here on Earth. So if you ever think about what NASA JPL do, for instance, NASA's Jet Propulsion Laboratory is a US leading center for robotic exploration of the solar system. They essentially create robots like the Mars rover that operate in completely different physics environments. As a result, they need to use simulations to be able to replicate those environment parameters. NASA JPL have been using Robomaker to be able to spawn their rover in simulations and be able to test multiple different scenarios and even build new capabilities, such as a potential robot arm for manipulation of objects. It's worth mentioning that NASA JPL have created a scaled down open source version of the rover that you can download at the URL on this slide and build both in a simulation or the physical robot itself using the bill of materials provided. So now that we've created that virtual representation of our robot arm and we can spawn it into a simulation to perform some testing, we now need to provide the robot with some level of capability. To begin with, we need to be able to recognize objects that we potentially want to be able to pick up and move. What we could do is use Amazon's recognition capability within our robotic application, which would provide our robot with an image or object recognition capability to be able to recognize objects without having to have that machine learning background or experience. And we can run that capability in the cloud, which means that we don't actually need to cater for the hardware footprint required on our robot. We can offload the resources required to AWS, and as a result, have a smaller hardware footprint for resource-intensive tasks. Now, one of the difficulties here for us is that we need to be able to determine the location of objects detected. While Amazon Recognition is able to detect objects, we're unable to use it to determine how close or how far away that object is. For that reason, we need to use a different capability for object detection and depth perception. So you may not have seen this in the very first demo that I did right at the start of this presentation, but in front of the robot, we actually had a depth sensor, or what's called an RGBD camera. You'd be fairly familiar with this if you have a games console at home that has a motion sensor. The camera we're using, the specific camera that we're using has the same sort of technology where we're able to layer depth information on top of an actual image, pixel by pixel, so we can determine where everything is within that picture. For this, we can leverage a package provided by the open source community that uses OpenCV to be able to recognize objects. Now, what you can see in this picture on the left-hand side is basically what the camera can see and has recognized. It might not be very clear, but essentially it's drawn boxes around two objects it's recognized, one red and one green. And then on the right-hand side, we've got the RViz console that we talked about before, where it's actually pointed out where the camera is and where those two objects are relative to the camera. So it's basically built out a map that we can use, that we can then use for our robot to determine where those objects are. So now that we've worked out basically where the object is that we want to pick up, we need to provide our robot some level of movement or kinematics. To be able to do this, we can use the Move It framework. This is a framework that operates on top of ROS. It's actually used for a lot of the manipulation capabilities that occurs within ROS projects, and it provides capabilities such as motion planning, manipulation, collision checking, and kinematics. And it does this via a number of different methods. The first method is using forward kinematics, which we're essentially defining those joint angles specifically in the arm to make a specific movement. Now, this obviously has certain restrictions. It would require us to put an object in a specific location every time to be able to make that exact motion. It's still quite useful for activities where you know that the object is going to appear specifically in that location every single time. But for our use, we want to be able to recognize an object, determine its exact location, then navigate the gripper to that object. So we're going to need something a bit more dynamic. For this, we're going to be using what's called inverse kinematics. The way inverse kinematics works is it's a bit more dynamic. Basically, in our scenario, for instance, we're able to place a can in front of our depth sensor. It's able to determine the 3D coordinates of the can in the form of X, Y, and Z coordinates. It passes those coordinates back to the robot, which then uses what's called an inverse kinematic solver, or an IK solver, which is an algorithm that's able to take those 3D coordinates and then translate them to joint angles that are required to make that movement to the can. So essentially, once we've tested out our robotic application, we can then use AWS Robomaker's fleet management capability to deploy our robotic application to our hardware over the air. We register our robotic hardware to the fleet management capability, and we assign its endpoint to a robotic fleet where we might have more than one robot specified. Then we can push down updates or deployments to our hardware. If you're familiar with AWS's IoT offerings and services, the fleet management capability that's provided out of AWS Robomaker actually uses AWS's Greengrass over-the-air update mechanism. So what we'll do now is we'll actually switch over to a demonstration. I'll just load up the screens from Robomaker that I've preloaded here. So what you can see here is a robotic application that's been launched into a simulation. And what we have here is basically 4 screens. These 4 screens represent 4 of the managed capabilities that Robomaker provides. So the top 2 we've already talked about. In the top left-hand corner, we've got Gazebo, which is the managed simulation. And what you can see is a robot arm that looks pretty much identical to the one that we saw earlier in the demo right at the beginning of the presentation. This is actually an open source robot arm called the BCN 3D Moveo that was created to provide an educational platform for engineering students to use as a cost-effective platform to learn on. The bill of materials as well as the 3D printable parts can be downloaded and used in your own projects. Basically, it's a 5-jointed robotic arm, and to the left and to the right of that, you can see down here, we've got 2 stands. These are part of the Gazebo world that we've created, and we can place objects on these that we can potentially manipulate. Now, a bit further back, we've got this depth sensor, which admittedly is floating in thin air. So one of the things to remember about Gazebo is basically you're lord of the world. So you can dictate that gravity applies to everything in the world except for potentially one object, which admittedly I've done here because it was easier than creating a stand. Now in the top right-hand corner, we have RViz, which in this case looks very similar to Gazebo. This is a 3D visualization tool, which allows us to visualize the robot. You can actually see a marker over here for where the gripper is, and that allows us to move the robot around and test its movement if we want to test it from a visual capacity. But more importantly, a bit further down, you can actually see that it's built out what it can see in Gazebo in the form of an octomap. So it's seen those 2 stands to the side of the robot, and it's built out that representation in RViz. So it's basically using that to notify the robot that these objects exist here and they may be collision objects or something that you might want to manipulate. Now to the bottom right, we have simply a Linux shell, which we're able to use to invoke scripts or check on processes. And then finally to the bottom left, we have an area where we can run a number of different plugins, which we'll get to a bit later on. But essentially we'll be running the visualization tool here, which will allow us to see what the depth sensor can see. Now, I'm actually going to be using scripts to move around the robot in this demo because it's just a bit easier due to the limited amount of screen space we have, as you can see. So first thing I'm going to do is move the robot arm to the right. Pretty simple movement. Kick off that script. So these scripts are actually all written in Python. You can also write them in C++ if you prefer. And you'll see in the top 2 windows that there was some movement. You can see that the robot arm moved to the right in Gazebo. You can actually see a transparent image that's looping of the robot arm moving in RViz. That's its planned motion. So it actually does a plan before it does the movement to ensure that it will be able to reach its destination successfully. And that planned motion is continuously looping. We can actually see that when we do a plan to the left. Let's do that now. So you'll see in the top right-hand corner that it's going to move, or at least do a transparent looping movement to hover over the other stand on the left. Obviously, it doesn't actually move in Gazebo because we haven't issued the execute movement command. All it's doing is planning that movement, and it's obviously taking a pretty standard movement to go to the other side. Now, what happens when we actually spawn a wooden box between those two stands? So you can see there's a wooden box that's appeared out of nowhere between those two stands in Gazebo, sort of sitting on top of the base of the robot arm, and the depth sensor has actually picked it up, and you can see in RViz that it's created that octomap of what it can see. It can't see the sides of the box, hence it hasn't created, I'll just move in a bit closer, it hasn't created the sides of the box there, but it can see the front and the top of it. So obviously, if we were to execute the previous plan, that's not going to quite work because there's a box now in the middle. Unless we want to smash right through it, we're not going to be able to execute that movement. So let's do another plan and see what happens. So we've executed the exact same script as before. No extra code was required. And we can see that it's actually detected that there's an object in the way, specifically the box, and it's replanned to accommodate that collision object. So what we can actually do now is move the arm to the left. And what we should see is it go up and over that box. And it does so. And so this gives us the ability to avoid that collision object, which is pretty handy without having to change any code at all. So what we're going to do now in the simulation is launch our object recognition tool. So you can see on the bottom left-hand side, just launching another window. Great. Okay. So on the bottom left-hand corner, you can now see what the depth sensor can see. So it's looking straight on at our robot with the box in the middle. And what we'll do now is actually delete this box here. Oop. And we'll spawn a can. So you can see that there's a can that's dropped out of the sky. It actually has the Amazon logo on it, and you can see that it's landed on one of the stands. It's additionally recognized that object. So you can see that there's a square, a red square drawn around that object, and it correlates the picture that it can see, so specifically that Amazon logo. Oop, it's just, oh, there it goes. It's recognized it again. It seems to be faintly recognizing it, but anyway, it correlates to, so it's sort of coming and going, but basically, what it's done is it's been able to detect a can that's landed on the stand with the Amazon A on it, And as you can see in the left-hand side of the screen, we've got a picture of that can as well. So it's been able to detect that. It's object 36. And then in RViz, you can see that it's actually detected that object 36 and that it's sitting on top of the stand. So it's been able to detect the object and it's been able to determine where it is within the 3D coordinates. So now we can essentially use those 3D coordinates to be able to pick up the can. So with that invoked, we should see this octomap, which is the collision object here, disappear. And we'll see a manipulation object instead, which you can see. It's basically a green bar, which is exactly where object 36 is. And we've got some movement. So interestingly here, you can actually see that the can was slipping out of its hand, out of the robot gripper's hand a bit due to that movement as it whipped it around. And these are the sorts of intricacies that you can work on in Gazebo. You can dictate things like friction or inertia or mass, which could all potentially affect your ability to move an object from one location to another in a rotational movement. But as you can see, it's been able to pick up the can and move it to another location. So what we'll do is we'll take a quick look. Where are we? We'll take a quick look at what that looks like in the physical simulation. Now, before I play this, this is a recording of the physical robot, the one that we saw at the beginning of the presentation. But what we've done is we've deployed the exact same code to the physical robot. Now, the way it works is we've actually got some stepper motors that are actuating the joints in the robot arm. And the way this works with ROS is that ROS publishes those joint angles for each of the joints. And we've created a driver that's able to convert those joint angles to the number of steps these stepper motors need to take to reach that joint angle. So for these motors that are in this robot arm, for those 5 joints, there's usually about 200 steps per revolution of the motor. And you can break down those movements to a 1/16 of a step. So you could actually do some very fine movements with these stepper motors, which is why they're used in things like 3D printing. So that's essentially the way it interacts with in ROS. So what you can see here, admittedly, part of the screen is cut off on the far left, just once again because of screen real estate. But what we're doing here is we're now actually moving that marker around because we've got a bit more space for the gripper. So we can move the robot around to different poses, and then we can plan and execute those movements for the physical robot arm. And what this allows us to do is to ensure that the driver is working correctly and that our algorithm that converts those joint angles to the number of steps required is spot on. So you can see that we're doing a number of different poses there, and we're moving it back to its original default state. Now what we're doing here, you'll be able to see some familiar screens as we saw before. You've got RViz in the top left-hand corner, and you've got the physical robot in the bottom right, which replaces Gazebo. But then also, you can see to the bottom left and the bottom center, both an area to be able to run scripts, as well as the object recognition capability, or what the depth sensor can see. You can see that it's recognized object 35, which is the can. It's determined its specific location within the XYZ coordinates. And then the robot arm has been able to navigate to that location, grasp the object, place it on the other stand, and then return back to its default position. So that gives you an idea of how you're able to pretty much use the same code to be able to execute the same sorts of movements and testing, both in a simulation and then deploy that to a physical piece of hardware and have the exact same results. So hopefully those demonstrations provide a bit of an understanding of some of the benefits of using AWS Robomaker for robotic innovation and development. Probably the most important benefit for myself or for anyone beginning this journey is around low-cost robotics innovation. So the fact that you can use the platform to simply get started, dip your feet in the water and determine whether this is something that you're going to be able to do or not in a pay-as-you-go fashion will allow you to build up the confidence to potentially put down some money for some robotic hardware. Another benefit is the ability to run safe simulations in multiple scenarios before deploying your robotic application to hardware. For some members of my family, they found this probably more important. The thing with the robot arm that I built is that it's about 10 times the size of that toy robotic arm that I initially bought, and probably about 10 times as powerful. So the good news is that it didn't cause any harm to any more furniture because I was able to perform test simulations in a safe manner within the cloud before deploying to hardware. Another benefit is being able to deploy a ROS workspace out of the box. You don't need to be a Linux expert to get started. If you were to use a local workstation for development, you would most likely need to dual boot, install Ubuntu, install a bunch of software frameworks. But this all comes out of the box with a few clicks in AWS Robomaker, and you can simply get started straight away. You're able to use additionally, you're able to use cloud resources for resource-intensive work. So if you want to build a chat capability into your robotic app, you can use Amazon Lex. Or if you want to build an image recognition capability into your robot, you can use something like Amazon Recognition. And then finally, an over-the-air update capability that allows you to deploy to fleets of robots is included in AWS Robomaker, which is a great capability if you're an organization that's looking at continuing to use robots in your organization and need a method of managing updates and rollouts. Now, for some of you that come from segments or industries where robotics is yet to be widely adopted, you may wonder where something like this could potentially be used in your organization. Now, the good thing about Robomaker is that it's not just for building robotic arms. You can build any type of robotic application that you want. So if you come from emergency services, for instance, you could potentially build an autonomous drone that's able to perform search and rescue missions. If you work in construction, you're able to potentially build a humanoid that's able to do automated assembly or build a mobile manipulator for bricklaying. If you work in hospitality, you could even create an autonomous vehicle that's essentially a kitchen or oven on wheels. So basically, if a customer calls to make an order, it's already cooking it up on the way to making the delivery, so it's fresh out of the oven when it gets to its destination. If there's one thing I'd encourage you to do after this session, it's to jump online and take a look at what other organizations are doing around the world in your segment or industry, because you'd be surprised at how much is going on that flies under the radar. So how can you get started with robotics on AWS? Well, I think the first thing is to start by thinking about how robotics could disrupt your industry and what problem it could potentially solve or automate in your organization. Once you've got an idea, it's time to start learning the robot operating system. There's a few great resources on this slide, as well as some community events to get involved with. Once you actually start creating your robotic packages, it's worth double checking open source repositories to ensure that you're not reinventing the wheel. And don't forget to check the Robomaker sample applications to get a head start on your development. One thing that I want to end with, essentially, is looping back on that conversation that I had with my friend mid last year about how robotics could potentially assist those with mobility difficulties. Now, admittedly, this robot arm, it's incredibly heavy. It's not very mobile. It's been painful lugging it around between conferences and user groups. So it probably doesn't fit a purpose for mobility specifically. One thing I can say with certainty, though, is the fact that basically the things that I've learned along the journey to be able to build this capability have sparked a number of other ideas that would be more fit for purpose. So for instance, the depth sensor could potentially be used for things like collision avoidance in a motorized wheelchair, or for instance, there are a number of other capabilities that could be defined. So I think for me, building this sort of capability and coming up with those ideas is the definition of innovation. Being able to get hands-on with the technology that was previously unavailable to us and getting a better understanding of the art of the possible. Thank you.